And so now you have 100x less overhead from the mitigation techniques and 10x less from the orchestration. That's how you get the 1000x difference in time and cost.
Is quantum computing trapped behind a hardware bottleneck? While we await perfect fault-tolerant systems, the software layer just might let us punch above our qubit count weight. Find out how enterprise R&D teams can extract massive value using current quantum computers in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is the CEO of Haiqu, Richard Givhan. Welcome to the show.
Thank you, Konstantinos. Thanks for having me.
Yeah, it's great having you here. We're going to dive right in with a little bit about the hardware bottleneck inside of quantum, just to give listeners an idea of where we're going here. So the main narrative has been that hardware limitations, adding qubits, coherence times, that's kind of like what controls the industry. So you've stated that the real bottleneck for enterprise R&D is the time and expense required to design and prototype experiments. So why has the software layer been historically undervalued? And how's Haiqu reshaping this perspective?
Well, historically, and for context, when Haiqu began in 2023, I think there's been a battle between two perspectives to applications development in quantum. One of those perspectives has been, let's call it theoretical cynicism, and the other, let's call it, dumb empirical optimism. And, in the former camp, which was definitely the sort of dominant camp for a long time, the assumption was that you would need to run exact, fully logical algorithms to do anything useful. So you would need full fault tolerance to do anything useful. And the issue with that is we won't have that sort of hardware for a very long time. Even for the next decade or so, we will have partially corrected quantum hardware in which some operations are logically protected and some still require mitigation and other sort of physical methods to mitigate them. And so, if you were a fault tolerance or die perspective, then you wouldn't think the software was undervalued. You'd just think it was stupid. You'd think it was dumb. And the reason is you would assume that, the only thing that was interesting to you is to focus on error correction, to focus on developing new logical algorithms, and to sit on your hands and wait for appropriate hardware. It also implicitly assumes that hardware goes from being noisy and completely useless to noiseless and super useful, which, to many people, the instinct was that actually there should be some interim regime where you can do something useful. And so I would say Haiqu and some others, for example, IBM, had a different ideology. I would say we were very ideologically opposed to this idea of sitting around and waiting an arbitrarily long time for perfect hardware. I mean, quantum computing is supposed to be a societally positive thing once it's useful. And so why not try and speed it up? Why not just see, can we do something useful on hardware that is pretty noiseless, but not perfectly noiseless? And so the idea was just to be more empirical and see what you could do on the hardware and see if any useful applications emerged. And that was how we started. And, we came to develop new methods around loading real scale data on a quantum computer, on reducing the depth of algorithms of programs such that they could run within the constraints of quantum computers, and on using different techniques to reduce the effect of noise on the resulting calculation, and ultimately orchestrating all these things together. And in doing so, we found generally, and other people have found, that you can do a lot more on these devices than the more theoretically cynical people had expected. And And so, what Haiku stands for is to accelerate the industry as quickly as possible with a suite of useful tools to do more. And I think now there is, perhaps begrudgingly for some, the expectation that we will do useful things on noisy and on partially corrected hardware soon. Arguably, there's already scientific advantage, but from a
Mhm.
commercial advantage perspective, it seems we are moving towards that. So I would
And
say the dumb, blind optimists, empirical optimists are winning right now, but let's see.
so, and we're going to get into a major software thing when we talk about your Agentic Quantum OS in a minute as a teaser there. But first, like as a specific example, you've given benchmarks that you can do a molecular dynamic simulation that used to be like $30,000 in 9 hours on classical, it for $25 in 30 seconds. So if you can just give a little
Mhm.
bit of detail of that, just so we can understand how that kind of impact is achieved.
Yes, and to answer the tail end of the former question, because you asked about time and it's related here, if
Mhm.
you assume that useful applications will be discovered empirically on near-term hardware, then the time that it takes to discover them is a function of the number of R&D loops you can do. And so if you give the tools for people to get a nice result on hardware more quickly, you're speeding up that process. And it's related here because what we wanted to show is that you can run sort of
Mhm.
frontier scale simulations on hardware for a lot less money with a lot less time. Why is that important? Quantum teams have limited R&D budgets and hardware is super expensive. So if you want people to make progress, you need to make sure they can make progress for less money with less time. So in this case, this was like a disordered Heisenberg model. Doesn't really matter. Our tools work on everything, but this was just a useful industry benchmark. And there was a big paper, front cover of Nature Physics, where they ran this nice simulation, and it took about 9 hours and I think about 30K, and it used a unbiased mitigation method, which ultimately will converge on the true expectation value with an arbitrary amount of time, a lot of time.
Mhm.
Um, and we don't have that much time, so we wanted to show that you could use a combination of biased and unbiased mitigation methods with considerably less overhead to get the same answer. And the way we got that outlandish result is because the overhead of the mitigation methods we were using had on average 100 times less circuit overhead. So that's how you get two orders of the speed up. And then the orchestration, the combination of those methods is non-trivial because they each might produce, a tree of circuits. Let's say a mitigation method uses randomized compilation. Each method might produce this set of circuits. And now you have this exploding tree of circuits that you need to run. The dominant factor on the cost is never the samples or the shots, it's the circuits. And so our orchestration, makes sure that you are never redundantly running the same circuits. If you have two mitigation techniques that both use the same randomized compilations and produce the same downstream circuits, you don't want to run a duplicate circuit. You just want to take what you've run and use that as an input into the other mitigation method. So it's a circuit reusability within the orchestration that gives you the other 10x. And so now you have 100x less overhead from the mitigation techniques and 10x less from the orchestration. That's how you get the 1000x difference in time and cost.
And just so listeners don't think of this as purely like in a lab, done for a paper, and that's it. Is this the kind of thing, this orchestration that's available to people? Like, can they start experimenting with this for their use cases right now?
Great question, Konstantinos. Yes, it is. It is fully available. It is productized. It is in the SDK, and all of your favorite teams are using it right now. Right now, it is on our back end, but in a release coming soon, the user will have full control over the runtime chain and also full customizability soon as well, where they'll be able to create their own quantum software module and
Mhm.
just stitch it into the runtime chain in an easy layer-wise fashion. So it won't just be visibility or usability, it will be controllability as well.
And helping along all of this, I'm assuming we get to AI, right? Because you guys are building agentic intelligence into your entire platform. So,
Right.
so how do your AI research agents, how do they like assist, let's say, an experimenter, a scientist, whatever? How do they go
Yeah, it
from like
all,
the research question to, a circuit, one of your optimized circuits?
right. So it comes down, why have we chosen this agentic path? It's more than
Hmm.
a buzzword. It ultimately comes down to the question of speed. What the OS does, what the runtime layer does, the tools you can access in the SDK, is it makes sure that when you have a high level application, you can run it performantly very quickly without needing to design and orchestrate the middleware yourself. So you save maybe 50% of your time there.
Hmm.
Now, in the design phase, how can you speed that up? That's where the agentic tools come in. And the issue is to develop a quantum application. It's pretty hard. It takes a lot of work, and it generally takes a lot of different faculties. You need domain expertise. You need a knowledge of quantum algorithms. You need to know how to produce a high-level quantum circuit and then optimize it and run it and so forth, interpret the results. That is a lot of time, and generally one person does not own that full suite of skills and expertise. And most teams do not have that full suite of expertise internally either. And so it can take right now, businesses will budget about 6 months to do one POC, generally at a toy problem scale. Let's assume that we have commercial advantage within the next 2 years, which does seem plausible now. Let's also assume that not every application you try empirically on the device is going to yield a commercially viable application. That's definitely true. So if you have 2 years and you're taking 6 months to do one POC on one topic, maybe you have a team doing some nice things in parallel and you're doing two POCs at once, right? So you're doing two POCs every 6 months and four in a year. Within 2 years, you've only tried 8. And that's definitely too few. And now you have to also continuously update those as the hardware evolves in scale and in maturity, for example, as it becomes partially corrected. So if you
That
think
last
about it,
step
there's a
for your
lot of
back
hidden
end target.
variables.
Yeah.
So you need an intelligent system to help you design these applications, as quickly as possible, but in a way that's constantly evolving. And that's what the Agentic OS is supposed to do. And so, you can imagine the R&D process as a graph of sub-processes, where you ultimately start with an idea and you get an executable circuit and a result. Some of those sub-processes can run autonomously and you don't need to occupy your researcher's time on. For example, you need to do a literature review, or perhaps you need to establish classical baselines and classical benchmarks to compare the eventual quantum method to. That is something that right now the Agentic OS can do autonomously. There are other processes within your R&D flow that you would like to do collaboratively. And so it might be, the design, let's say you're trying to design a new ansatz or a new feature map to do quantum machine learning with, or really to do feature enhancement for machine learning with. The literature and the review and the classical baselining you can set about autonomously, and then you can have an agent work with you collaboratively on the design of a new ansatz. And you can say, okay, give me all the expressibility metrics from the literature. Give me all the approaches from the literature. What are their shortcomings? And this is where the superiority of human abstract reasoning capabilities comes in. It is still the person that makes that logical leap to get to the new exciting idea. The Agentic OS just gives you the tools to prototype it very quickly, make sure you're not doing anything that's already been done before, and run it on the hardware as quickly as possible. It has a good command of the Haiqu tools and all the other tools that are out there in the industry. So it helps at every stage of the process. You have individual agents working on individual sub-processes within the R&D. It lets your team collaboratively work on different parts of the research process, and the agents will share context across related processes. It's a nice system. We're excited for people to try it.
So a couple of like mini questions connected to this. One, when it comes to like quantum talent, does this let you bring in more junior people into, let's say, a project because it'll do so much of the heavy lifting for you? It'll kind of teach you along the way, spot your errors. Is it that kind of thing?
Yeah, it's very helpful. And I would also like to say that Haiku is, I think, really good about hiring younger people as well. This is just a tangent, but I'm just going to let the industry know. And the reason for that is sometimes younger people are more willing to take risks, empirical risks, and are not sort of overly specialized from their PhD and 2 postdocs. So they can be a very useful personality to have within the team. And these tools make them stronger because it gives them access to all the relevant domains within their R&D process without them having to have done a specialty in it. And then it gives them access to the downstream quantum software engineering know-how. So it would help anybody, not just a young person. It does act as a rising tide for anybody within the team. I think it is probably the most enabling for the researcher category of person. So somebody with a great theoretical command who either, doesn't have great quantum software engineering skills or just doesn't want to. There are a lot of people, who begrudgingly have to do the prototype code.
Mm-hmm.
And, researchers are notorious for producing spaghetti research code. So this definitely helps that, helps them get to where they want without the same painful process.
Does the Agentic OS learn from the experiments people are doing?
Yeah. So just to, ground it, because, right now it sounds like a buzzword, Agentic OS, and it is a buzzword.
Sure. Mm-hmm.
But what it actually means is you have a foundation model. You have a
Mm-hmm.
series of prompts that Haiku has written that tell the foundation model how to behave. And then you have a knowledge base that the foundation model can reference to understand how to do what it does. And, why would you use Haiku and just not go use Claude? Why would you not just go use Claude? The reason is the Haiku knowledge base has all of our know-how from the last few years of applications development, and you're able to answer things more quickly, to demystify scientific nuance more easily, and generally produce a useful result. It also knows, and it's been taught, how to use all of our tools and all of the other tools in the industry as well.
With the Agentic OS constantly improving and learning from the user base that you for the information base that you said is being created, I'm assuming then that there might come a time when it can do almost all of it, right? Like, because it's going to have so many examples, so many previous user submitted examples. Is that true? Like, would it get to the point if you do 100 optimizations for companies or whatever over time, that'll just be like, oh yeah, your data set kind of fits these 7 examples I have. Let me just pick the best one for you. Is that like on the radar?
Yeah, I mean, basically the goal is to bring every team to the practical frontier as quickly as possible and to keep them there.
Mm-hmm.
That is generally the goal of Haiku, but it's the goal of
Yep.
the Agentic OS as well. And so, yes, it gives you a unified place to develop your applications and to continuously evolve them. And the goal is to build the smartest quantum research assistant in the game.
Mm-hmm.
I think you will always need some level of abstract human reasoning ability, at least until you have AGI. But I don't know when we're going to have AGI, and I don't think we have it.
Yeah, that's fair. Yeah, I wanted your
Not to
take because there are
disparage what
yeah.
AI can do, but it can
Vibe
do
coding is
amazing
becoming
things.
a thing, right? So I was
Right.
just curious how how you view that.
I view it as a research assistant, and I think it
Mhm.
will still be able to perform most of the functions within an R&D process, but you will necessarily need the reasoning capabilities of a very strong researcher to make the leaps necessary to get to commercially viable applications. but it will just speed up the cadence, the result cadence for those people considerably. And those
Yeah.
people can, basically reserve their focus for the hard thinking and not for, okay, how do I approximate this part of the circuit? What mitigation technique should I use? Blah, blah, blah.
Yes. And you're constantly updating those, right? Like you're constantly working
Yeah.
on things like suppression, error suppression, et cetera. Isn't that, and of course depends on which back end target you're using. So you guys are integrated with the cloud. Like how are you, how
Yeah.
fluidly are you working on this, like going forward?
Yeah. So most of our team is doing internal R&D for the software core of the product. So that's still where most of our focus goes, is developing new methods to improve performance and figuring out how to optimally combine them and teaching the AI how to optimally combine them as well. So yeah, how do we connect to cloud backends? In the same way as, basically every other product, we are built on classical infrastructure, for example, on AWS. And then if you want to run on a quantum computer, right now it's a bring your own token model.
Mm-hmm.
So you can run via AWS with an AWS token, on IBM with an IBM token, and we can connect you to all those backends.
And so whenever a new processor comes out, let's say from IBM, you're going to have to examine how to get the most out of that, right? Like how, down the stack.
Yeah, but we're always running tests to figure out
Oh,
what's
okay.
best. And so by the time the user is trying something, we have a good sense. But for a lot of research questions, it's good for the user to just try multiple modalities.
And you've used the stuff behind the scenes to do some of those papers and things that we referenced earlier. Can you give us a little deep dive into the SKQD work that you guys have done?
Yeah. Um,
If you could like
so
set the
first of
stage for
all,
people. Yeah.
SKQD is a cool algorithm because, to my earlier point in the podcast, it emerged out of a more empirical approach to quantum computing. Implicitly it says, okay, I understand the limitations of a quantum computer. I can't run an arbitrary number of operations. So how can I derive benefit from it within what it can do? And it uses the quantum computer, SKQD does, as a sampling engine. So it's a state generating machine that you sample from, and then you use classical computing for the
Mhm.
downstream diagonalization. It's a nice algorithm. We really recently did some work with it, uh, mostly as a chance to showcase the prowess of the Agentic OS. And the reason we did that is because it's a frontier method, and also the benchmark we did it on it's a difficult benchmark. It's the single impurity Anderson model at 40 qubits, and there was no code availability. That was actually the big reason, right? That we chose that benchmark, is there was no code availability. There were benchmarks, there were claims. It's a well understood hard model. So can we reproduce SKQD on a difficult model with just our agents cracking away with a little bit of help from Haiqu? And the answer was yes. And we could even improve the result. So yeah, can I answer any particular question about SKQD or what we did? What do you want to
Yeah,
know?
I mean, so it's a problem. You were solving a problem in condensed matter physics, right?
Yeah.
So, and as you said, there wasn't a lot to build on, so it became more of a pure, I guess, scientific test. How would, I guess the simplest thing for listeners would be to understand how something like this whole, using the whole idea of quantum and HPC combined, right? Like, nothing is pure quantum. Everything is classical hybrid with quantum. How would this be applied in the real world, just so they can get a sense? I think that'd be the easiest way to handle
Okay.
this.
I will go through it pedagogically.
Hmm.
So what you want to do is find the ground state energy of a system. Why do you want to do that? Well, it tells you a lot about, I don't know, maybe the uh, reactivity of a system or other properties. In materials, it might tell you something about the magnetic properties or electronic structure. In this case, we took a kind of very typical model in condensed matter physics, which people are very interested in. And we said, okay, can we find the ground state? That's generally what people want to do. Why would you do it on a quantum computer? Well, if you wanted to do it classically, what you would do is you would take the Hamiltonian, which you know analytically, which is the total energy operator. So it basically encodes the interactions within your system, what's coupled to what. And it's a really big matrix. It's a huge matrix that encodes all that information. And you want to throw that matrix into some diagonalization algorithm, and you want to figure out what the eigenvectors are and what the eigenvalues are. And the eigenvalue here, because it's the Hamiltonian, represents the energy value. And so the lowest eigenvalue is your ground state energy, and the corresponding eigenvector is your ground state wave function. So why not do it classically? Well, those matrices get really big. And so in the model we did, which was this 20-site Anderson model, that corresponds to a matrix of dimension 2 to the power of 40. So you cannot throw a matrix that large into a classical diagonalization algorithm and get a result. It's too big. It's too big, generally speaking, to instantiate into memory. So it's not that this is classically insimulable yet. If you exploit, for example, some symmetries and other techniques, you can probably crack it classically, but it's near that boundary line. However, if you get to, I don't know, 60 qubits equivalent, then suddenly it's unsimulable. So it is a hard problem.
Mhm.
On a quantum computer, why would you use a quantum computer? Well, you can sort of, instead of really struggling to hold that matrix in memory, you can physically instantiate a state on just 40 qubits in this case that represents
You're 2 to the
that time
40.
evolved.
Yep.
That state time evolved
Mhm.
under that Hamiltonian, which shares the same basis. So that's what you do. It's a very easy way to produce this analogous thing in memory. So now you have this quantum state that represents that information that you can efficiently produce. However, the quantum computers cannot um, cannot run enough clean operations to run a diagonalization algorithm on what you've now encoded in your quantum memory. And so for that reason, you need to say, okay, well, now I can instantiate the information here in this nice quantum state, but I can't run a quantum algorithm over it because VQE won't converge and because QPE, has too many operations and won't run either. So what I'm going to do instead is I'm going to sample. I'm going to sample from the state that I have. And why am I going to do that? Well, I know that these different states, there's multiple states that you produce, by the way. You take an initial state, which the only condition there is it can't be orthogonal to the ground state. As long as it's not orthogonal, maybe use Hartree-Fock or some other method, but you produce some crude initial state, and then you time evolve it under the Hamiltonian. So you have a circuit that represents like e to the minus IHT for different time steps. And you time evolve that state under the Hamiltonian for different time steps, and you produce these states that each contain some amount of the ground state wave function. And you sample from those states. And by sampling from those states, if the ground state wave function has a lot of amplitude to it, then you know that the samples that you're getting out in the computational basis are a decent basis to describe the ground state wave function in, because that state you're sampling contains the ground state wave function. And you need to sample multiple states because you don't know how much of the ground state is contained in which, and it changes depending on the time step. If, for example, that you had somehow instantiated the ground state itself, then no number of new states would benefit you. You would only need to sample the ground state, right? But you don't know that, so you sample multiple. So so that's how it works. So you sample multiple of these states. You pull out these samples. They give you a new computational basis, now a much smaller one that can describe your ground state. And you say, okay, I'm now going to evaluate the analytical Hamiltonian that I have. We're now going back to the analytical Hamiltonian that we have with respect to these new computational basis bit strings that we've pulled out. And in doing so, I'm going to form this new matrix and diagonalize it classically and try and find the ground state and the ground state wave function in an approximate way.
Yeah, my first thought when I was reading that was when we do something like 60 or 70 qubits, because of the sampling, will we be able to defend it and say, oh, this is advantage?
Yeah.
Even with this technique, it's still advantage. So I don't know if you had any thoughts on that.
I would say it's an open question. Verification is a
Mhm.
very hard problem. I don't have a prepackaged like, yes, absolutely, here's a nice way to do
Yeah.
it. Um, but yeah, I expect people have better opinions on this than me, to be honest.
So it's funny. Like when you listen to your answer, your explanation of it, um, the idea of taking like the samples and everything, it almost like reminds people of the early days of like compressing audio or something,
Hmm.
right? You're creating a certain kilohertz wave, and then you're compressing it afterwards. I mean, isn't that something like what you're doing different anyway when it comes to compression?
Well, yeah, I mean, in this particular case, the goal was to say, A, can we reproduce the code that would simulate this model? And then can we improve it with the existing tools in the Haiku SDK? And the relevant tool here is the compression, the circuit compression.
Hmm.
And the reason it's relevant is because you're trying to sample from these different time evolved states. And all that means is you are now applying deeper and deeper circuits. For a further time step corresponds to a deeper circuit that you need to run. It's harder to run. You get corrupted by noise. And so our thinking was, well, maybe we can compress these circuits for the deeper time steps. And in doing so, we are able now to sample deeper time steps and get higher quality samples to form our basis than otherwise we would be able to. So, yeah, with respect to the audio analogy, it's about finding a compact representation of the same state. Um, it's almost the same state. It's approximately close. It probably generates slightly less entanglement because you're dealing with less circuit depth. But in the battle between, total accuracy and the corrupting effect of noise, it is a more successful approach to take a slight approximation of the state you would like to sample, but be able to sample it more cleanly because you haven't run as many operations and therefore haven't been as corrupted by noise. I'm losing now the audio analogy, but
Well,
in the
yeah,
sense that
it's
it's a
just
compact
to let
representation.
just to let you listeners kind of get a sense of that we've been down this road before in a way, this idea
Yeah.
of not capturing the whole thing, basically. And no, that's clever. And when you want to apply this to other industries, like how can we see some commercial value from this? Like what kinds of use cases? Maybe finance, maybe
Yeah.
drug discovery or whatever. What do you see coming next like that?
Okay, so let's frame it this way. You have these different classes of applications. Let's say you have three, really broadly. You have this class of application where you're using quantum computing as a sampling engine. And these are
Hmm.
probably the most near term because they're the least demanding on the quantum computer. And then you have the applications where you're also running the algorithm on the quantum computer, and either that algorithm is non-variational or it's variational. So those are the other two classes. Sticking with this class, this sampling engine based class, you have SKQD and you have feature mapping. So you have, people are using it in machine learning where you're taking some input data, you're taking a QML ansatz, you're mapping that data now onto quantum state space, and you're measuring it out, and that those constitute new now classical features for you that you push into downstream machine learning or into downstream quantum machine learning if you don't pull them out. But yeah, these sampling techniques, like if these sampling engine-based problems are viable, they could be viable super soon because you can already load data at the requisite scale, in parentheses with Haiku, but you can. And so let's take SKQD. That lets you find the ground state of different systems. That's very useful for understanding material properties. So if you are working on, I don't know, electronically correlated materials, or you want to learn about high temperature superconductors or things like this is a really relevant approach. Even if you're trying to do optimization in finance, if you map it to one of these problems where you're trying to find the energetically lowest state because that corresponds to the optimal value, suddenly this is useful to you for feature mapping, which is the other one of these sampling based approaches. That could be useful for a whole host of things like fraud detection, but generally anomaly detection problems or problems in which the data set is very high dimensional, very difficult to learn over. And there's certain problems that have smaller data sets where you have a very high dimensional hairy data set with that is smaller, that your classical machine learning methods struggle on because of their expressibility, but also just because there's a lower scale data set. And, that concerns problems like more extreme fringe cases of fraud detection, for example, or maybe material property classification in a lab where you're producing empirical lab data sets, right, that correspond to physical qualities. So I would say, yeah, in the sampling engine category, that's what you have. You have SKQD and you have this QML based feature mapping. And then you have those other two types of applications, which are not as easy, but there are still algorithms that you can run today. For example, LRQ-AOA. You can run 100 plus layers of LRQ-AOA on 100 plus qubits with Haiqu today. And there's other things you can do too.
So, I mean, I heard your answer earlier about verification being difficult and all that. I was going to ask you what you think would signal the true arrival of practical commercial quantum advantage to close this out. I don't know if you have an answer for that, but if you do, I'd like to hear it. And also as like a follow-up, let's say IBM's right and they think they're going to have fault tolerant now by 2029. Like, whoa, that's really close. That we're going to have really amazing machines. That's their latest bet. How does your approach change then? So like, do you take better advantage of this machine with your approach? Like, so I don't know. That's kind of like a high question.
You do. You absolutely do. Because you won't have full fault tolerance for perhaps around a decade. What you'll have is, some set of operations being fully protected by error correction codes. And it's all up to some amount, 9 nines or whatever. But then you will have some operations that require too much coding overhead to protect. And so you would use more physicalist methods like mitigation. And so really for the next while, we're going to have, let's call them early fault tolerant devices, but they're partially corrected devices with some hundreds of partially corrected qubits. Those sort of systems require a combination of error correction with, mitigation, approximate methods, circuit compression, etc. And so you will need a software layer that can combine all of those tools and orchestrate them. And that is exactly what Haiqu is building. So, it'll be very relevant. You will not have a device where you can run an arbitrary program on for probably a decade or so. And so, you will need to consider the constraints, and that's what we do. In terms of, and also that's the OS, right? Like, there's more nuance here where let's say you have an application, let's say it might use different types of algorithms or just one algorithm, you're still going to need to know in context what the best error correction code is to run a particular algorithm. And I think the user is going to want control over that. And so there at a higher level, the user is going to need to think about, okay, how do I protect the information for this type of algorithm, this type of application? The Agentic OS would help them there. Our tools would help them there. In terms of quantum advantage, how do you know? You kind of know when people get really quiet. Right now, the incentive is to generate press and to say, my business is doing incredible things and is approaching this very strategically powerful position of achieving nice computational advantage. That is definitely a worthy press remark. Once it becomes real, you do not have the same incentives to talk about it. You don't want your competitor to know that you're about to, especially in finance, for example, where the bottom line is incredibly obvious. This goes back to your earlier question of like which domains will experience it. It's not just a function of when something useful works. It's also a function of how long does it take for let's say you're doing drug discovery and you do a nice simulation and you learn something. You might still need to encounter 10 years of clinical trials for that knowledge to become a viable product. In finance, that time to value is truncated because if you have an algorithm that, for example, calculates risk a little bit better or optimizes portfolio a little bit better, it immediately touches your bottom line and there's no process in between. So, when people have advantage, it's when you expect them to go really quiet and stop talking about it, which is already happening a little bit. Other than that, it's just about repeated commercial use. Right now, we have sort of single time demonstrations. But, if you have people running things that are even incrementally better repeatedly in production, to me, that constitutes commercial advantage. If something is useful enough that you would repeatedly run it, that's commercial advantage. And so what would you expect to see, as an outside observer? Well, you would expect to see consumption revenues of companies increase because people are running more on devices. You would expect to see the cost of hardware decrease because you're running more on devices. So, this is how really you would probe, is there commercial advantage in the industry? It's how much are the devices being used.
So in other words, that there's commercial advantage and you just don't want to tell me. No, I'm kidding.
Yeah, well, that's how it's going to be though. Like people won't tell you but they will just be using the devices more.
Yeah. So with that, I'll let you go. Thank you so much for explaining all that. And I do encourage people to take a look. We're going to have the show notes containing all the info and how to check out Haiqu. Thanks, Richard.
Thanks, Konstantinos.
That does it for this episode. Thanks to Richard Givhan for joining to discuss Haiqu. And thank you for listening. If you enjoyed the show, please subscribe to Protivity's The Post-Quantum World and maybe leave a review to help others find us. Be sure to follow me on all socials at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protivity. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protivity.com or follow Protivity Tech on X and LinkedIn. Until next time, be kind and stay quantum curious.